Yeah, thank you, Jimbo, for having me and very nice introduction. So I'd like to actually, as Jimbo mentioned, to talk about how I actually get started with the video intelligence. So I get started building video intelligence about 10 years ago. And at that time, mostly I think people have been working on design neural network architectures. So essentially, for example, we have the 3D commonness, which is essentially doing convolution not only over height and width, but also over the temporal dimension. And then in the late 2020, people have been essentially working on using different kind of like data set for training these neural network as for video like recognition, video localization. And the first data set we have been working on is the so-called UCF data set, which is of 101 categories. It's not that long, just few seconds, but you have a lot of fun with that. And then we realized it's important to make the data size scale larger so that you will be able to train more powerful action classify and video models. So that there it comes this kinetics 400 data set, which covers actually 400 different action categories. And then at the end of the 2020, it looks like saturated. I mean, the accuracy, whatever, this kind of performance on the kinetic data set also kind of like saturated. And then we wanted to still, upgrade and make the video models stronger than what we should do. And natural idea is that can we still try to scale up the data? But that actually would be quite difficult in the sense of for UCL kinetics, people actually manually verify the labels and involve a lot of annotation efforts. And if we wanted to annotate at an even large scale, that's quite label extensive. So how can we get more supervision? So I guess that's really marks the start of this era of multimodal or whatever you name it, like self-supervised or unsupervised or weakly supervised. But essentially the idea is on YouTube, we have so many video data. It's just how we can get the labels, the supervision. And fortunately on YouTube, these videos often come with the transcript, which is essentially not very precise aligned, but in some kind of like loose manner aligned with the visual content in the video. So it provides some kind of like weak guidance with supervision for us to train video models. So this is a data set from ICCV 2019, which is called How to 100 Million, essentially 100 million videos on YouTube teaching people, like this kind of how to do something. So in this talk, I will basically mainly talking about the research problems that we have been studied within this video language interplay problems. And the first one I'd like to talk about is actually from the video to language, which is essentially the task of video understanding. Like given ChatGPT or Gemini video, now you can ask questions and it will give you answers, textual answers. So that's kind of like mapping the video to language. So what does the, as the 2025, what does the sort of state-of-the-art video understanding look like? So let me show you this demo quickly. It's a paper upcoming on this CVPR 2025. We essentially, it's a video LLM model, and then it asks to do this kind of narration for incoming streaming videos. So the input is only video contents, but the output of the LLM is the description of what's happening right now at this moment. And also we use a off-the-shelf text to audio synthesized model so that it can actually generate audios. So let me see how can I play this video.
Way,
you can hear this
release,
sound.
live, say, hi, speed. Welcome. Welcome to the Toyota Center in downtown Houston, Texas. First round between the number 2 seeded Houston Rockets and the number 7 seed Golden State Warriors. And here's a look at the starting lineups for both teams. Curry, Podziemski, Moody, Butler, Green, Van Fleet, Green, Brooks, Thompson, Sengun. Here is Thompson. Got it. The Rockets lead by 2. Hey guys, today I will show you how to fix a water-damaged laptop. So if you've got a laptop that's been accidentally spilt on, or you've dropped it in a puddle of water, this is what you need to do. First of all, you're going to need some paper towel, and you want to use this to wipe down the entire laptop. Next, you'll need a pentalobe screwdriver, and you want to unscrew all the screws. 8, 7, 6, 5, 4, 3, 2, 1, and lift off of the Falcon 9 rocket.
Yeah, so I hope you get a sense of essentially how powerful these video M nowadays. They can essentially not only narrate the video content, but also do very good kind of OCR tasks and also do all this kind of thing in real time. So diffusion is very powerful, but most of these video M models, they are trained on the internet videos. So they are good at this kind of videos I just shown, but they are not so good at actually the egocentric videos, which is the video actually we perceive with our eyes. And also, if we want to build out the smart glasses or robots, the video is often of this egocentric perspective. And the challenge is also not only lie in the egocentric, this kind of egocentric direction, but also if you take a look at the video from Ego 40, actually the camera motion is quite significant and it's not that stable, so it changes often. And then a natural question to ask is that, is there a domain gap when we trying to adapting these models trained on internet video to egocentric video? Because that's the kind of like the large scale pre-trained model we have, which is on pre-trained on internet videos. So how does that perform on egocentric video? So we started that in our paper, this so-called ego VLP, egocentric video pre-training. So essentially there is indeed a domain gap. And in this paper, we were trying to mitigate this domain gap and make the first video language pre-trained model for egocentric video. I'm actually not going to the very details of this work, but I'd like to highlight some of these contributions and interesting stuff. So the first thing we need to think about, or when we get started with the problem, is that, okay, now we want to train an egocentric prediction model. So this is the first thing we need to have is essentially data, right? So at that time, what we have is like charades, Disney World, Epic. They are of actually this kind of scale. So in terms of number of clips is usually 30K, 90K something. So it's not as the scale of a million, which is the scale people often use for pre-training internet videos. And fortunately, at the time, we had this Ego 40 data set, but it's actually of the raw videos, which means that it could be like 40 minutes, 15 minutes long, and a lot of events happening in this video. So in terms of doing this video language pre-training, we need to have video text pairs. They are essentially the trimmed video clip that aligned with the short language sentence. So in this world, we curate a data set essentially based on Ego 40 that is called Ego Clip, which is of about 3.8 million video text pairs. And with that, we have the data, the video text pair to train the video language model. And also there are some other couple of design we have. For example, we have this so-called Ego NCE is essentially a training objective specific design for this egocentric video dataset and the this like Ego clip kind of like data format. And also we have a Ego VLQ MCQ, which is essentially an evaluation dataset used to benchmarking how good is the performance of different kind of like method design. And with this data model, then we would be able to train really the video language model for egocentric video. And once it has been trained, we can transfer it to different downstream tasks, like the video text retrieval on application, like action recognition, charades, and also a bunch of tasks on Ego 4D challenge, like natural language query, which is essentially give a textual description, and then we wanted to find out when is the start and end time of this event that has been described in this sentence within a very long video. And you can see for this egocentric pre-trained model, it can improve the internet pre-trained model by quite some significant margin. So by the way, any questions so far?
No, it's good. It's good, yeah.
Okay. Yeah, sounds good. So this is about actually the video to language. And then another problem I've been working on, as Jemo mentioned, is actually for language to video. So it's like Sora kind of like thing. And I was trying to show a video demo to, about the video generation. And then probably Sora has been kind of like, we have get tired of Sora. So let me show you this interesting video clip, which is actually what we call impossible videos. So we are actually creating a lot of videos that appearance-wise looks like realistic, but as human beings, we can tell that it break out some kind of like physical laws, etc. And I think one interesting thing is that if you post the video, then you probably cannot really tell this is AI generated, it's so realistic. But if we play the video, then you can get a sense of, okay, this is definitely not true. So video generation nowadays is quite powerful, but also is quite expensive in the terms of the compute. And when we get started with actually the video generation, that's in the 2022, and many big companies at the time get started with the video diffusion models, and they train the video diffusion models on thousands of GPUs and then for maybe several weeks. And for universities, we probably definitely don't have this kind of resources. So but we are still trying to work on this problem, and then we are thinking about what should we do. So this sort of like pushes us to think deeper about the question of what might be the minimal things that we wanted to learn for video generation. So any quick guess maybe about how does this video generation consist of? So a quick guess we had at that time is it could be actually a combination of appearance and motion. So essentially, if we have an image generated already, then the only thing left for video generation is that we wanted to add on to inject motion to make it move. And for appearance, existing video diffusion models, they can do pretty good job already, right? Like for stable diffusions, and if you have a texture prompt, Spider-Man on the beach, cartoon style, then it can generate these different kind of like possible images, which all align with the text and looks realistic. And then now the problem is how we can learn this minimal thing, the motion. So we had a hypothesis at the time is, okay, if we can reuse the image diffusion model for the appearance generation, so perhaps the only thing left for us is to learn the motion. And for the human beings like us, we are actually pretty good at this. So by just looking at this one single video of a man's skin, we can imagine what does actually a Spider-Man skin looks like. So how can we kind of like adapt this kind of similar paradigm for models to let model have this kind of like similar capabilities? And if we can do that, then we only actually need to train on one single video instead of train on a lot of different videos. So this motivates us to do this work, so-called turn-out video, one-shot training of image diffusion model for text-to-video generation. So the pipeline is like the input data is actually only a pair of video and text, like a main skin. And then we repurpose the existing text-to-image model as a text-to-video model. So essentially, you expand the temporal dimension and duplicate a couple of times a long time. But for the parameters, these all can be duplicated. And then for this paradigm is essentially train these video diffusion models on the one single video text pair, and the output once the function is done, then you get this text to video model. And then during the inference time, you can manipulate to change the text prompt, like change it from a main screen to like a Spider-Man skin on the beach, etc. And then it will generate the video of very kind of like similar motion or pattern with the reference video. And this can be done very quickly on just 10 minutes and only need just one single GPU rather than hundreds. And here are more of the kind of like examples, like a rabbit is eating a watermelon on the table. So you can kind of like remove eating a watermelon. Essentially, it will actually remove this like big object out of the video. And also a puppy is eating a cheeseburger, comic style, change the watermelon to a cheeseburger. And this is an example about a man is dribbling a basketball, and you can change the person into like James Bond or other kind of like style like Lego man. Okay. I need maybe quick questions before move on or okay. So yeah, so this is actually I like to give a very brief introduction of what is video understanding and what is video generation. But you know, I have students working on video understanding and another student working on video generation, but they sort of like do not really talk to each other, kind of isolated problems. But but as human beings, we actually with one single brain, we can do both understanding and generation with one single brain. So how can we actually improve the interplay between these two tasks? And what does the maybe actually the next generation model look like? They may be actually a unified model that can do both the understanding and the generation. So that's our hypothesis, and then we develop this kind of work, which is called Shou, which is essentially a one single transformer that unify multimodal understanding and generation. It was released last year summer and just presented last month on the iClear conference. So the idea actually behind this work is we want to do unification. And this idea has also been explored already, like in this work so-called NestGPT, which is can do like any-to-any modality mapping. So given this LLM is actually fixed, is frozen, and it can take in modality like text, image, audio, video, and then the idea is that it can not only generate text but also generate this like image, audio, and video. And what makes it possible is that it connected through this image diffusion model, audio diffusion model, video diffusion model to do the generation. So it's bridged to be connected throughout these projection layers. So using the projection layers, we would be able to connect LLM with diffusion models and make this kind of like any-to-any mapping. So this is kind of like a unified system, but still the LM and diffusion model, they are two isolated models. So then if we take a further look at the models, like for understanding all kind of like is, you know, nowadays is like, for example, lava model is of a transformer diffusion, is a transformer model. And it takes in like visual as input, language token as input, and then output language tokens. And if we take a look at generation model, and you have probably like the diffusion transformer, like stable diffusion, and it takes language as input and output the visual images. And it also, not recently, there is also kind of like LM-like or autoregressive manner generation models, which means that it really operate at the so-called discrete token level. So given the language as input, we would first predict what does the the first patch or first token of the image looks like, and then using this as the input of your LM to predict what does the next visual token looks like. But the common thing for this stable diffusion 3 or llama gen is that they all build upon transformers. So now, since all of these models are actually transformers, so it would be possible to just use one single transformer to unify all these kind of different things. And so there we ask this question and trying to explore that. And also, meanwhile, there's some kind of actually concurrent work or prior work did this kind of explore this idea. And there is this work called large world model from UC Berkeley. So it's actually of the autoregressive manner and adopting a kind of like a large language model manner to take in not only the language as input but also the visual images input, and visual images going through VQGAN to convert into some image tokens. So usually like 16 by 16 tokens. And for the output, it can not only output the text tokens, but also can output the image tokens. So in this way, like when the first different images that comes in, then you would be able to predict what does the tokens of the next frame looks like, and so on and so forth. And this is still kind of like a very early result. And then there is this work called Chameleon from Meta, actually released make this idea more concrete and scale up it on some real world task. And this is quite exciting. In this example, you have the input prompt like, what can I bake with this? Give me the full receipt and show me an image of the final dish. And it appended with an image, which is this one. So with this image and sentence as input, it can generate this very long actual recipe. And at the end of this output, this response, you have actually an image appended, which is this one. Actually, the model actually would be able to imagine what does the final dish look like. And how this is made possible is actually through this what they still call this autoregressive model or LM model. And the input, you have the text prompt and the image prompt, and image prompt goes through the image token to tokenize into some kind of like indices, like 1, 2, 3, 4, 5, these kind of like indices instead of the continuous vector representations. And based on these indices, it's of kind of like similar manner of how people deal with text tokens, which is also of this kind of indices of 1, 2, 3, 4. So they can do this kind of prediction of text and also images. And once we reach the end of the image, which is essentially the input is done, and then it start to do prediction. And firstly, it predict a text token, and with this text token predict, it fit into the LM to predict the next text token. And at some point, it can start to predicts this star image token. So then it marks the start of the prediction of the first image token, second image token, so on and so forth. And each image token will go through the tokenizer to actually be mapped into the real image patch. So this looks like awesome. But this way, this kind of like paradigm is all based on autoregressive. And comparing to diffusion, autoregressive is actually quite slow. Like for example, typically for one single image, we will divide it into 16 by 16 patches or tokens. So if we do the one by one prediction, then in order to predict one single image, we need to do 256 times prediction, go through this network for 256 times. But for diffusion model, you actually just go through the network once. I mean, you probably still need to do a few iterations, denoising iterations. But for DDIM, it's only just it's 50 iterations typically, and for some latest technology like flow matching, etc., you probably just need 3, 5, or at most maybe 8 iterations. So it's quite fast. We don't need to go through the neural network so many times, comparing to autoregressive. So this motivates us to think about how we can actually use diffusion. And this is not actually that straightforward at first, because for popular diffusion models, like for example, stable diffusion, it all works in the so-called latent space, which means that given the real world image, you will first pass through the encoder to get vector representations, which is a continuous vector. And we do this diffusion, essentially denoising process on this like continuous vector. And this one is actually the reconstructed vector. But for what actually the autoregressive model does is based on the indices. So it is like these tokens we predict here is all this kind of 1, 2, 3, these kind of like indices is rather than kind of like a vector. So how can we do diffusion modeling on these discrete tokens? essentially this becomes kind of like a not so straightforward problem at that time. But when we actually look into the literatures for kind of a more machine learning perspective, we can find out that not only people have developed theory for continuous diffusion, which is the one we are more familiar with, given a random noise, and we are trying to gradually recover each individual pixel values and get a clean image. There are also another paradigm, which is the discrete diffusion. So the paradigm of discrete diffusion is actually we sort of like divide this. Still, you have kind of like a black image or this mask out image. Then you would divide it into some very small grids like this one. And then in each iteration, we would predict or reconstruct some of the masked regions, masked grids. And then finally, we would get the full RGB image. And for the discrete diffusion, actually, let's introduce a little bit more about its details. So given this image as input, we actually would be able to chunk into, like for example, 16 by 16 grids. And for each patch or each grid, we kind of like can go through this tokenization process. And then you get like a sequence of tokens. And for this sequence of tokens, it has corresponding state transition matching. So essentially for the column, essentially for each row is corresponding to each indices, each token here. So for example, for the first token is corresponding to the first row and can be actually transit into these k+1 possible states. So K is essentially, so there are actually K+1 columns, and the first K rows corresponding to these different K status. And the last one is the so-called master state, which is the black hole essentially. And if you do this kind of derive the variational lower bound and the learning objective, it will look at this. Pretty much actually consists with the continuous diffusion. And what's more interesting is that this discrete diffusion paradigm can be even simplified, which means that we can add on very strong constraint that each image token can, during this transition process, it can only either stay unchanged, which means that transits into itself, or replace with the mask token, which is actually the last token. And for all the other possibilities, all the other categories, we actually do not allow, and you can just remove that. And this actually ends up with a very simple kind of like mask token prediction paradigm that have been used in the previous mask GIT. So for mask GIT is actually work that developed by Google in 2022 CVPR. So the idea is, when they did this work, the idea was also trying to speed up the autoregressive process. And for example, for autoregressive transformers, it needs these 255 iterations to predict one image. But for this like mask GIT, because we are predicting these masked out regions, and it's actually quite fast and can achieve a good image within just 8 steps. And this one was conduct experiment on ImageNet, and then people further scale up it on the text to image generation. So given a text prompt, you can generate these like fancy images. So this kind of like gives us some kind of evidence or confidence that this mask GIT or discrete diffusion can still do very well in terms of generation. So why not we just do that in our unified model? So here's a kind of like a summary of the motivation idea. Essentially, for doing unified modeling or for understanding generation, there are works that like NextGPT, which is essentially having two separate diffusion model and LM model. And then recently we have like large world model and chameleon, which would be able to take in language and vision as input and output language vision just within one single model, one single LN, but it's based on autoregressive. And for our model, Shou essentially is also one single model, but it's integrate autoregressive and diffusion. So when we are trying to predict language or dealing with the text tokens is essentially autoregressive. But when we're dealing with the visual tokens is diffusion, so it's faster. Any questions so far?
I think we had a question in the chat from a little earlier.
Oh, yeah,
I think
let me check. Sorry.
Yeah, I think this was from right after the tuna video slide.
Yeah, how many degrees of freedom for the human motion are using? Sorry, which actually the video was referring to?
I think it was after you presented a tuna video.
Tuna video. Oh, I see. Yeah. So for each actually, yeah, let me just to open the chat again. Yeah. So essentially for the 1 second. Yeah, so for this kind of like turn out video, because actually this is actually a very good question. So we would be able to do like changing the object, changing the background, all this kind of I think all the kind of editings of the appearance that would be possible actually with this turn out video schema. And for there actually, because for our model is actually still requires one round of fine tuning. There works actually later on proposed that would be able to do the so-called zero shot editing, which in the sense of it does not really actually require training and can directly edit the reference video into some kind of like other appearance. But for that one, the freedom is actually much less. Because for example, if I have a dog, I can probably change it into kind of like cat or something similar to essentially the skeleton of the dog. But if you change it to something else very different, like a human or whatever, then you probably feel. But for our message channel video, is actually can do much better in this kind of like large change of the object shape. So I hope that addressed the question.
Mike, I have another question. Can you hear me?
Yes.
Yeah.
Yeah.
So for diffusion, you do need a conditioning, right? For the generative video or images, the diffusion process needs some kind of guidance or condition, right?
Yeah, right. Yeah, for especially like the
Right. So where does the guidance come in from the text part? I didn't quite get. So you mentioned the discrete diffusion, but where is the guidance that for the diffusion come in?
yeah.
Process.
Yes, good question. Yeah, so for this one, on the ImageNet, actually the condition is the image class. And for this one, which is they actually extended to text to image generation, so the condition becomes text.
Is the text encoded somehow, or are you using the autoregressive output of the latent variables to condition? Or are you using the text itself, then you go through the encoder, then going to this?
Yeah, yes, correct. So for this text to image, then we need to go through some kind of test encoder to get a vector, use that as a condition.
I see.
So
that directly send in a latent variable from your autoregressive model to the image generation.
Yeah, right. So so this is actually what is done in this Muse model, but for our model, actually it's a little bit different. So for actually, yeah, this is a good question. So actually, I'm going to introduce more details about this one. What we actually did with this autoregressive plus diffusion.
Okay, yeah, go ahead. Yeah.
So this is actually a kind of like a giant figure, but probably no need to read that. The only idea is to show that this framework is unified, can support a lot of different tasks. And And it's quite actually flexible in the sense of you can support any kind of like input and output, which means that any kind of like combination of the text token and the visual tokens, as long as you unify them in the text prompt. So for the corresponding to Jambo's question about what is the condition we have been using here, then for different cases, then we have different condition. For different tasks, we have different condition, but all of them will be essentially convert into these tokens, which are indices, and then we based on the input and then trying to predict what is the next indices. And for this Shou model, actually, we'll be able to support both the autoregressive and diffusion. And this is referring to the mechanisms of the attention, actually. So by autoregressive, what is more specifically in terms of implementation is that we use the causal attention, which means that the token can only attend to the previous token, but cannot see the future tokens. But for diffusion, actually, every token would be able to see each other. So let's take the multimodal understanding as an example, in which is essentially kind of like we create a problem given this image and some of the questions, and then we are trying to predict the answer of these questions. So we can organize the input in the way of like start of the image. There are some kind of special tokens, like MMU indicate this is a multimodal understand task, and then start of image, end of image, and these are the actually image tokens. And then we have the start of text, end of the text, and this is corresponding actually to here the some of the question, the sum of the text in the question will be actually put over here, and then we are trying to predict these dark blue text tokens, which is the output. And if we take a look at the attention map here, because we start with the image tokens, and for the image, is actually every image token will be able to attend to each other. By the way, this is the attention map of the attention map of these like attention layers we used. And for the text tokens is of this like causal attention, so you're only able to attend to the previous tokens without seeing the future tokens. And for the visual generation, so the input here would be kind of like is essentially a sentence. And again, we organize it into like this kind of specific format of start of text and end of the text. And the text tokens are in the between. And then you have the start of image, end of image, spatial tokens. And in the between is the image token we are trying to predict. So because for diffusion models, then we need to have, if in the continuous diffusion case, then it's actually, you need to provide some random noise. And in the discrete diffusion case, actually it's essentially this black area, which are masked out the tokens. So we are trying to essentially to recover, to predict what does this masked token looks like. And essentially trying to predict the indices of these master tokens. And the condition would be actually the previous text tokens indices.
So
and
my question, yeah. So you conditioned on the text token, but the text token had to be encoded, or just text token itself is a condition?
Yeah, it has to be encoded. So go through a text encoder, and the text encoder will map, like for example, the specific text into a number, the index.
So it's like so it's like the cross attention and the stable diffusion, or
yeah.
Can we just use since you're doing autoregressive modeling in the text, can we just take some of the generative encoder layers directly input to the image generation?
Yeah, I think that's also yeah, interesting. Yeah, that's definitely very interesting idea to do that as well. I think that the reason we use these indices rather than latent representations is because we wanted to start with some existing LM models. And for the existing LM models, they do this kind of like first tokenize into indices.
Okay.
Yeah, cool. Thanks for the question. So actually for this visual generation or this, there are two cases that are particularly interesting for Shou kind of like model, which is the in-painting and out-painting. So for this task, like a dog sitting on the beach, and then this is the image actually we are trying to edit to manipulate, and then this is the mask provided by the user. So the idea is trying to mask out this region and then predict or change this region into a dog sitting on the beach. And in our framework, this is quite natural that for the image tokens, we can still keep the background content here. Only need to mask out the center kind of like these tokens in the mask out region, and then recover and predict these mask out tokens. And because we are actually doing this like full attention, so when we recovering the tokens inside this mask out region, it will be able to see every other contextual tokens. But if we in the conventional autoregressive manner, they are you are only able to see the previous token without seeing the future tokens. So some future tokens here we would not be able to have access to. And also similarly for extrapolation outpainting, essentially the idea is that we can consider the outer area to be extrapolated as the mask out tokens, and then predict or recover this outer mask out region. And another interesting task that can be done with this Shou kind of architecture is the so-called mixed modality generation, which is the video keyframe, essentially the video keyframe generation along with the text descriptions, which means that we generate output not only in just video, but also for each video frame, we have a textual description along with the kind of like the transcript. So here is an example that slicing avocado, and then with this, so the slicing avocado would go text here, and then the image tokens are here. And then we will actually first predict the sentence of the first frame, and then this is done in an autoregressive manner, and then you could do the diffusion to predict to reconstruct the images, and then so on and so forth to predict the text for the next second frame, and then also the use diffusion to predict the second frame. And in terms of the attention map, this is kind of the causal attention for the text, AR for the text, and then diffusion for the image, and then for this comes to the second frame text and the second frame's image. So I guess in the interest of time, I will not go into much details of the experiment, but just share some of the insight and the highlights. So one quick highlight is that the model we use is actually the so-called 1.5 model, which is actually quite small. It's only 1.3 billion parameters. And we for the training data, we basically just using the open source, the academia or public data set. And one questions or maybe one thing that we would be pondering about this unified model is that whether it can be, although we unify two things, understanding and generation into one single model, but can it still be as good as the understanding only model or generation only model? So that requires to first kind of like a baseline, which is only, for example, in this case, for multimodal understanding benchmark, then we have a baseline which is only doing understanding, only trained on understanding tasks without learning any generation capabilities. And these are some of its benchmark numbers. And for our Shou model, and we can see that it actually can achieve pretty kind of like comparable result to this baseline. So although just one model, it can support generation, but it can do as good job as the understanding only model on this multimodal understanding benchmark. And for also it if comparing to other unified model, you can see the previous unified models are actually quite large, like 7B, 13B, etc. And our model is just 1.3B parameters, and it's actually in some cases comparable and even better than these large models. And here is a benchmark for generation. So essentially very similar conclusions comparing to the other unified models. Although our model is much smaller, the results is even better or comparable. And also it achieved quite comparable results to the generation only model, which use a lot of training data, but for ours only kind of like 35 million images compared to the previous models they use like quite a lot. And here are some of the images actually generated by our Shou model. You can see it's quite diverse and interesting. Like there could be even a close-up view of a computer screen with the screen displaying a web page or some of the paper artwork, etc. And this one is of 224 by 224 resolution, and we also support 500 by 500 resolution. And here, this is a result for the impending, essentially, given this input image, also providing the mask that we are trying to impend a blue sports car with sleek curve and tint windows. And this is an example of impending the exploration. So essentially the outpending. So given this input image and put it in the center, and then we would imagine and reconstruct what does the outer regions look like according to the sentence, the continuous mountain ranges and jungles with middle river condition appearing. And here is an example for the mixed modality generation, which is the joint generation of the video keyframe and the caption essentially. So given this input image and with the bacon frying, then we have the firstly, the person is preparing a bacon in an air fryer, and also you have the image along with it, and bacon on a piece of the paper next to an oven. And more interestingly, you could actually provide some kind of like, questions for them. Like user asks a question, can you guide me through making avocado and apple juice? And then we start with this first image of the apple peeling and cutting, then we'll be able to actually generate the full kind of like the sequence of or procedures of doing that. So back to the original questions, like for this work, we essentially are trying to think about what might be the next generation foundation model looks like, and show kind of like demonstrate it's very promising to use just one single model for both understanding and generation by unifying autoregressive and diffusion modeling. But there could be actually a lot of actually the open questions still, because it's just the, I guess, the start of this research of the unification. For example, for the visual tokenizer, should we use the discrete tokenizer so that it will get these indices, or like Jianbo just mentioned, like can we having maybe a latent representation vector, so essentially it still continues. And also there are some kind of like discussion, the research around whether for example, for Shou is of the autoregressive, unify autoregressive and diffusion. How is this comparing to just, for purely autoregressive? And will we go another way around, actually use just a purely diffusion models? And also for video, can we use Shou for kind of video generation? And also there are questions around, can we, 1 + 1 larger than 2? We are doing both tasks on the same generation. So can we see some kind of benefits along each other? For example, by learning understanding, can we enhance the image generated, video generated, and vice versa? So I guess I'd like to maybe talk about the second questions, and if they are more interested, I can go through other kind of like questions as well. So for DeepSeek, actually they also have a follow-up to show that it's also doing this unify modeling. And the very first version they have is the so-called genius flow, which is also of 1.3B parameters. And again, it used the autoregressive and unify with diffusion. More specifically, they actually use flow matching, advanced version of diffusion. But in their second iteration, they actually, this so-called Genius Pro, which is 7B parameters, much larger. So in this model, they actually switch back to use the autoregressive modeling for both image and text. So I think one of the reasons is that in terms of the engineering design and engineering implementations, right now, we are very good at actually LLM training technologies. And so we are, in terms of engineering improvements and setup, autoregressive is really easier to do in this when we're trying to scale up. But when it comes to diffusion and unify autoregressive and diffusion, there's still quite some work in terms of the engineering optimization. So for this like larger versions, they go with just the autoregressive. But interesting, there are also some work, this like so-called dual diffusion put on archive last year. So everybody for the text part, everybody were using autoregressive, but they are using diffusion actually even for text. So it's one single model and using text for both visual and language. So the result is promising, but you can imagine it's not that easy because nowadays all of the LM is actually based on kind of like autoregressive. So if we wanted to make this like diffusion work for text, they need to maybe first to have a diffusion model actually work for text only. But it's quite promising idea. And also recently, I believe maybe many of you have seen this GPT-4o model. Essentially, it's very good at this kind of visual language alignment, given this kind of textual description, a wide image taken with a form of a glass whiteboard in a room overlooking the Bay Bridge. The field of view shows a woman writing, etc. And more specifically, we can specify the contents essentially written on this whiteboard in the text prompt. That's quite impressive and is pretty very much actually aligned with what they wrote in the text prompt. And one interesting is that like people don't really know how OpenAI implement this, but there is probably a hint or in this like image with one big autoregressive transformer. So I guess that is pretty possible that this GPT-4 kind of approach is a unified model. So it's just one transformer, and first because of the trying to scale up, they go with the autoregressive manner. But this actually go back to the concerns of autoregressive, which is actually quite slow, which means that you need to predict the image tokens one by one. And this is actually indeed what we experience so far with the 4O image generation. So no sure, but maybe for the next generation, they would try to explore the unified model of like diffusion so that can go much faster. All right, so let me just skip this sound like videos generated by Shou models. And also it can do image animation, which is to convert image into videos. So far, I have been sharing about essentially the work of what we did, essentially trying to unify understanding and the generation into one single model. And this probably is what we are excited about at the end of 2025. And then I've been thinking about, okay, what should be the next thing we should do, right? So in the next 5 years, what might be the more promising directions? So if we take a bigger look at the history from 2015 to 2020, we are mostly working on supervised learning, UCL, kinetics, did come with human annotated curated labels. And then in the past 5 years, when in this kind of era of multimodal, we have been mostly working on the interplay between video and language. And then first, the next big thing is actually about action. It's really learning while doing, is to really interact with the environment and get the feedback from the environment and learning from them. And like many people have been actually doing kind of like this vision language action model for robot learning. That's one actually natural direction for working on, the actions, especially in the physical world. And also there are quite a lot of works nowadays recently posted that is to develop simulation systems based on video generation models to augment training data for robots, which is not that easy to collect, in the real world. And this is about actually what we have for, the physical world. And meanwhile, actually, there is another interesting domain for action is in the actually digital domain, which is the GUI agent. So essentially, as we are looking at this computer screen, it's coming actually a streaming video. And if we could have a assistant that kind of like looking at the streaming video and take control of our keyboard and mouse and performing some action for us, and then it can make our daily life probably much easier. And this is a demo we developed for this GUI agent. So actually for DBS is a bank statement in Singapore. So that's, like when we go for reimbursement, whatever, you always need to download a bank statement. And then every time I forget where should I download this bank statement and how to do that. So for this assistant, let me try to play this video. Oops, sorry, looks like I get started with this PDF. So just to make sure can you hear me or?
Yeah, we can hear you.
Okay, yes. Sorry, I guess yeah, the PowerPoint is there. Oh, that's actually a good showcase of that we need an agent to help with the GUI, the software. But yeah, since we are already at the time, never mind. So probably I can end up here. And if there are any questions, I'd be very happy to take.
Let's thank the speaker. Time for some questions. Anybody? So Mike, yeah, so looking at your system today, it seems to be still most of the parameters are in the text space, right? Because the majority of the parameters seem to come from the language side, isn't it?
Yeah, actually, this is also a very interesting question. So we indeed actually look into the distribution or contribution of, what kind of maybe parameters or neural network layers contribute to text, or in which part or portion of that contribute to language. So one interesting we found out is that in the bottom layers, in the early layers of this LM, actually most of them actually activated when there's image comes in. So they account really actually for visual inputs. But in the higher levels, then mostly the activations is on the text tokens. So probably these parameters in the higher layers are mostly for high level reasoning, so that is more related to text.
So the model you made right now is still text driven, I mean image generation driven. As you work down for video generation, where is the prediction of the next frame video bring to the feature extraction? Is the task of making a video prediction model harder, therefore force you to learn more latent space features?
Yeah, so there are actually a couple of challenges when we are trying to upgrade this Shou model for video. So the first thing is that, or actually it's a kind of like a challenge we add on for ourselves. So is that we don't want to have a separate image tokenizer and video tokenizer. So we develop kind of like a tokenizer that can work for one single frame generation, and also it can be used for multiple frame, essentially video generation. And also there have been some kind of like design rationale we have been thinking about. So for example, we could like, just like the conventional video generation models, that we could generate all the video frames together using the diffusion models. And the another way is that for videos, especially long videos, for us like human beings, we are not be able to imagine or generate this like 1 minute long video at the same time. So it makes more sense actually to do that at the frame level, at least in an autoregressive manner. So it's unlike the conventional autoregressive, which even do 1-by-1 prediction for image, but for this like frame level autoregressive, when we are generating an image, generating a frame is all the tokens are generated together. But when we have the first frame generated, then we will go to generate the second frame. So at the frame level, temporal level is kind of like autoregressive. Yeah, these are kind of like the two design kind of like rationale or challenges we were dealing with like when trying to upgrade to video.
Yes. Yes, can you hear me?
There's a question. Can you hear the speaker? The questioner.
Yeah, speak louder. Can you hear me?
Yes. It's just my computer kind of like screen is there and I cannot see you, but yeah, I can hear you.
Yeah. Oh, I cannot hear. Okay.
Yes,
Yes.
I have a question. That you mentioned that video generation is the appearance plus motion. So do you see it possible to like generate video based on the image and motion? So that's
Yeah, sorry, I think there's some echoes, but if I understand here correctly, so the question was like if we can do video generation based on one single image and also some dynamics of videos, right?
Like motion. Yes. Yes, you need to have some control for the generated models. So I wonder if the control can be images and the motion.
Yeah, I think that's a very interesting question, actually. Yeah, for like video generation, I think there are people investigating different kind of like control, like exactly, for example, optical flow. So for the reference video, like the one single video we used for turn video, people could actually firstly extract optical flow for this video and use that as kind of like a constraint or condition for the inference time for generation. So the generated video actually would be very well actually constrained and follow this optical flow. So that it will actually align with the motion much better. But also there could be, I mean, it could have it has pros and cons. So it's more aligned with the motions of the reference video, but also meanwhile, if we want to do more creative tasks, like and the change of the shape of the object is quite significant, then you probably don't want to add on this like very fine level constraint of the motions. So yeah, I guess like is a design problem of like what kind of like granularity we want to go with these motions to be added into the video generation.
Yeah.
Yeah, I guess I went on mute this time. Hi, first of all, thank you so much for the talk. I wanted to ask a question on also motion, but more on the physical intelligence and robotics and learning by doing that you mentioned. I just wanted to hear your opinion. I wanted to ask if you could give more detail about what specifics you find promising in this area and what challenges you think we need to resolve first.
Yeah, so yeah, definitely this is a very interesting problem to work on nowadays. So essentially I think people have different kind of concept nowadays, like world model or whatever. So essentially the idea is that it's not so easy to collect data for training robots. And when we are manually build up the simulation system, it cannot be so realistic as the real world videos, real world scenes. So what if we can actually treating this kind of image of video generation models as a simulation system? So there, actually, I'm trying to go back to my slide so that I can show the video clip. Give me 1 minute. Let me see if I can fix this PowerPoint issue. Sorry, never mind. I guess I give up on that. Yeah, but I can verbally describe. So essentially, for the simulation system nowadays, probably does not so realistic. So one way we can use the video generation model is that we can make it more realistic, like fix some kind of the artifacts. And also, we could use the text prompt to specify what kind of like lighting we want, what kind of like texture we want to be add on the objects, and also augment ones. For example, in the real world, we have like one single video of the robot capture recording, and then we can use that video diffusion models to change its appearance, change its texture, and maybe also in the challenge case to add on a few other objects to be interactive with. So that will augment the value of the training data very much. And then we use this all kinds of like generated videos, generated data for training the robot policy to account for the data sparsity issue.
Thank you.
Yes, thank you.
Okay, well, let's thank Mike again for a great talk. Yeah, thank you, Mike.